So the second part of the fundamental theorem of calculus we actually already know. We said the first part we learned, not that it's part one, but was that a derivative could undo an integral. Also, we can undo a derivative with an integral. So we learned to use an antiderivative to evaluate a definite integral in 5.3. And that's the second part of the fundamental theorem of calculus. If capital F of x is any antiderivative of little f, then the integral from a to b of little f is capital F of b minus capital F of a. Some quick examples. We did some examples in 5.3. You're going to see lots and lots of this on the AP test, especially the multiple choice section. Well, no, especially everywhere. And then we're going to spend all of chapter 6 learning new techniques we can use to find antiderivatives when they're not sort of the obvious ones, the ones you have memorized, or the ones that you know you can just add 1 to the exponent and divide by the new exponent. But this one we can do if I want to find the area under 3x plus 1 squared between 0 and 1. I can do that if I can find an antiderivative. Notice this guy, they're sort of trying to trick you, but you're smarter than that. You're not going to get tricked. If this were just a plain old boring polynomial, it would be easy to find an antiderivative. We would just undo the power rule like we did on that example in class today, where I gave you x squared and you had to add 1 and divide by the new exponent to get x cubed over 3. So notice here, if I rewrite this, you guys use the word FOIL, if I multiply this polynomial out, I'm going to have 9x squared plus 6x plus 1 dx. Then, let me get more room. So this is going to equal, I'm going to think of an antiderivative, and that's going to be 9x, we're going to add 1 to the exponent, divide by the new exponent, plus 6x, my old exponent was 1, so my new exponent is 2, divide by the exponent, plus the antiderivative of 1 is x. So that's like 1x to the 0, I'm going to add 1. I'm going to use that, I'm going to start to, from now on, use that notation that we saw in the last video, which is I'm going to evaluate that from 0 to 1. This is probably, like on a free response question, good enough to get 1 point. Typically there's 1 point awarded for finding the correct antiderivative. And this notation makes it clear that you think that this is an antiderivative. And then probably 1 more point for finding a correct result. We haven't evaluated this antiderivative. We haven't, if you excuse the expression, plugged in the 0 and the 1 yet. But once I do that, I can leave my answer and choose how much I want to simplify. Notice that I could simplify this polynomial first. You could have simplified it as you wrote it instead of leaving it like this, plus 3x squared plus 1x, evaluated from 0 to 1. I'm going to come up here just so I don't have to erase all of that. So that's going to be 3 times 1 plus 3 times 1 plus 1 times 1 minus, do not make this common error. I'm about to subtract that whole polynomial evaluated at 0. And well, in this case, it's not going to be a big deal because it's just going to be a whole bunch of zeros. I want you to build the habit now. If you're going to subtract something in calculus, that something is not going to be necessarily a very simple expression. It should go in parentheses so that we make sure that the whole subtraction gets distributed. So this is going to be 3 times 0 plus 3 times 0 plus 1 times 0. So this will simplify to 3 plus 3 plus 1, 7 minus 0. My final answer is 7. Remember that you know how to evaluate this on a calculator now. Feel free to type that expression into your calculator and see if it comes up with the same value for the integral. Okay, I really do want you to try to answer this little question A and question B. They're sort of a quick review question because they're going to be key to our understanding of really, guys, what I think is the most important idea in all of Chapter 5. It's going to guide most of the rest of our work in Chapters 6 and 7. It's going to guide your application to any interesting application of definite integrals. So the integral from 3 to 3 of tangent of t dt 0, right? Because why? Because my lower limit and my upper limit on my definite integral are exactly the same. So I'm finding the area under a curve between one number and one number. I'm finding the area of a rectangle with width of 0. This next one, letter B, is a review of the first part of the fundamental theorem of calculus that we learned. I can take the derivative with respect to x of an integral whose lower limit is a constant and upper limit is x, and whatever function I have on the inside just turns into that same function, but instead of being a function of t or whatever it was on the inside, now it's going to be a function of x. It's going to be tangent of x. So those were supposed to be easy. Quick review because they're going to help us understand this next big idea. So this comes from your textbook. It's page 297, example 4. Can you write a function whose derivative is tangent x and for which f of 3 equals 5? Most people at this point, they go back to thinking what we did in chapter 4. We practiced, maybe it's chapter 3. We did a little bit of practice trying to find our first antiderivatives. And we did that by trying to think in our head, okay, what function do I know? And when I take its derivative, the answer is tangent. Well, guys, there isn't one. This is not one of the ones that you know off the top of your head. And if you wanted to try to get an answer, it'd actually be kind of hard. We could do this, but it's not easy. So we need a different technique. And this technique is so powerful. Ask the BC students about the chapter 5 review test that they took. How many times did they use this important idea? So notice that I can write a function that incorporates these two ideas that I just practiced. I want a function whose derivative is tangent x. Well, why don't I write my function so that I'm integrating tan t dt. So check this out. As long as I make the lower limit a constant, maybe 0, maybe not 0, when I take the derivative with respect to x of this integral, I'm going to get that integral to cancel out with the derivative, and I'm going to have tangent x as my answer. Okay, so then the only other thing I have to worry about is how do I make it so that when I replace x with 3, the result, the output of the y function, is 5. And here's the answer. If I make that lower limit 3, then later if I use 3 as my upper limit, remember this example we just did, even though my face is hiding it? The integral from 3 to 3 of anything is going to be 0. That's okay, because now I just made f of 3 equal to 0, but I want f of 3 to equal 5. So what's the only thing I could do to my y function that's not going to change the derivative and can make the output 5 when x equals 3? Well, adding or subtracting a number here is going to not change the value of my derivative. So I just constructed a function who, if I took its derivative, what would y prime be? Well, y prime, the derivative of 5 is 0, and the derivative of this integral is tangent x. Okay, and when I plug, that's one requirement, the derivative is tangent x. The second requirement is that when I replace x with 3, I get 5 as the result. Well, when I replace x with 3, this is going to be 5 plus the integral from 3 to 3 of anything. The integral from 3 to 3 of anything is 0. So that proves that I'll get 5 as my result. This is a very convenient way to write a function whose derivative is some given function and which satisfies some, we call it an initial value, an ordered pair that we've been given. All right, so check out this cool problem. I know that there's a tree trunk, and if I were that kind of person who was going to cut the tree down, I would notice that if I cut it down, the shape that's left behind is a circle. So we call that a circular cross-section. This tree is perfectly round. Pretend. And I know something about the radius of that circle. I know this function. I know the rate at which that radius changes with respect to time. And I know this function is good from time 0 to time 3 years later. And I know that at the exact moment when my clock starts, time equals 0, the radius of that tree trunk is 6. So check this out. Write an expression involving an integral. That's your cue, that's your hint that you're allowed to use this new trick we just learned, for the radius of the tree trunk on the interval 0 to 3. That means no matter what time value I want, you should be able to tell me what the tree trunk's radius is then. That means that you need to write me a function of t. So there should be a t somewhere in your function. Use your expression then to find r of 3. And notice this is a calculator active problem. So here we go. We're going to haul out what I call the most important example in chapter 5. I need a function for the radius. Look, they've actually already implied that I should call it r. I need r of t. And what do I know about r of t? I know one ordered pair. I know r of 0 should equal 6. And I know r prime of t, or dr dt, is this. Okay, so I need my derivative to be dr dt, so I'm going to write, I could write dr dt here. What are my limits going to be? Well, my lower limit is going to have to be a constant. My upper limit is going to have to be, my upper limit is going to have to be t, so watch this. If my upper limit is t, guys, I cannot use a t inside my integral. Good, I'm going to find that this whole thing is going to be much easier if I just write this expression out. And I can use any variable I want except t. And don't use r because you're already using that to stand for something else. So I'm going to write 1/16. I have a small tradition in calculus of using p, because if we use p, watch what happens. This is going to be, it could be any letter you want, really, but not t, not capital R. It can't match the upper limit, can't match this function name. 1/16 3 plus sine of, if I make this p squared, what's this going to have to be? My dummy variable is going to be dp. Daniel Pearl. Okay, so, but any variable you want to use in there is fine. I'm going to have to figure out my lower limit. I'm going to have to figure out if I have to add or subtract a number here. So I want r of 0 to equal 6. That means I want that lower limit to be 0, so that if I replace t with 0, I'm going to integrate from 0 to 0. My 6 comes out here. This function, capital R of t, if I took its derivative, I would get this. If I replaced t with 0, I would get 6. Those are the two requirements for my function. Now you can actually use your calculator to answer this second part. Use your expression to find r of 3. So I'm going to write that r of 3 is going to equal the 6 plus the integral from 0 to 3 of 1/16 3 plus sine p squared dp. I'm going to type that into my calculator to get my final answer. So you can see what I've typed here. Let's see if I can show my answer. So 6.6108 is the radius of the tree trunk 3 years after time 0, the start of the problem.